So this is not a very advanced session. There will be some advanced things there which you can safely skip, right? So that's not going to be something which is going to stop you from understanding anything. Feel free to stop me anytime you wish, and if you want to ask any questions regarding anything in the slides or anything that you don't understand, feel free to stop me. So I don't think I have, so the timeline is I think 1.5 hours or so for lecture and 30 minutes for questions, but I don't really mind. I mean, you can make it, can flip it and make it 30 minutes of lectures and 1.5 hours of questions. I don't really mind. There is no strict agenda, no syllabus that I have to cover for your exam, no such thing there. So I do what is feasible, what you like. So it's really, there is this Tamil phrase called Neyar Viruppam, so and that's what I'm doing here. Whatever your subscribers like and subscribe, that's what I'm going to do here. That's all for the introduction session. So what am I going to do today is introduce some machine learning to you first. Probably take some 30 minutes. The most basic machine learning algorithm that you will see. And then some advanced tools, which is what is actually in the title of the workshop, ensemble methods. I mean, there is lots, I don't even remember what the title of the thing is. I think I remember those ensemble methods, wisdom of the many or something like that. So I typed something which Bharati asked, but I don't even remember the title now. But really what it tries to capture is how you combine several simple models, let's say, into one big model, one very good model. That's the idea behind ensemble methods. But before you do ensemble methods, you must know how simple models are. I mean, what are simple models? So that's what we will do in the first part of the lecture or workshop. And we'll move on to ensemble methods later on, right? So before I go there, I would like to know how many of you have done ML foundations, finished ML foundations? 1, 2, okay, a few. How many of you are doing MLF now? That's great. So that's almost the rest, all the rest of you. How many of you have are neither, right? They are not neither doing MLF now or have finished MLF. Okay, that's still a significant fraction. So of this third group, how many of you have finished Maths 2 and Stats 2? Okay, at least you have finished Maths 2 and Stats 2. So are there anyone here who have not finished Maths 2 and Stats 2? JK? Is there anyone who has not finished Maths 2 and Stats 2 also? Okay, that is a small population. Hopefully you have finished Math 1 and Stats 1. Right, so, okay, so that particular, okay, I don't think even you will find it difficult because I will skip over the difficult parts. So the easy parts is what will actually be left over. All right. Okay, great. So here is something which I have been using in my class lectures. I've stolen this from some really nice website. This is not done by me. Someone else has done all the pretty looking things. I'm just going to use just directly, I am accrediting whoever that is. I don't even know who those people are. But it's a pretty way to teach one of the basic tools in machine learning, which is decision trees. So if you have done machine learning foundations or doing machine learning foundations now, you have definitely finished week 1, where I would have introduced the basic problems in machine learning, that is classification, regression, and all that, right? So one of the basic problems there is building a classification model or a machine learning algorithm which does classification. So that's one of the basic tools of machine learning. That's almost what everyone means by default. When someone says, I have done machine learning, typically that's what they mean. That is, they have learned classification and they have used a classification algorithm, right? So that's the default assumption. That's almost the default model, right? So there are other models like regression, density estimation. Those are also used, but if someone doesn't say anything, right, that's the default assumption. Okay. So one of the most basic classification algorithms that are used is what's called the decision tree. Right? There's no need to lock the things. Let them come in. If people come, let them come. Or they can come through that. Oh, okay. So this is first introduce what's called the decision tree. It's a very intuitive algorithm. We will look at that first, and then look at how we can combine decision trees or other models into what are called ensemble methods. Okay. First off, before you even look at decision tree, what is for people who have not done MLF or not doing MLF right now, what is a classification task, right? So that's the first question I'll try to answer now. That is, you have a bunch of data. When I say data, you have a bunch of vectors. In this case, what you have here is a bunch of data on houses, right? So you have, let's say, 10,000 houses, and for each house you have, let's say, 10 numbers, or in this case, 7 numbers. What are those numbers? You have the number of square feet that house has, what is the price of that house, what is the height of that house, what is the number of bedrooms this house has, and so on, right? So you can imagine easily some 7 or 8 numbers that are associated with each house. You can imagine that. And in addition to these, let's say, 7 numbers, you also have one other piece of information, which is whether it's on the whether it's in San Francisco or New York, right? So these are just two. I mean, it can be something else also, but this is the data it has. It is whether this house is in San Francisco or New York, correct? So let's say somehow someone gives you these 7 numbers, but forgets now you have this data set of, let's say, 1,000 houses, and each house has 7 numbers. And in addition to that, you also have something saying whether this house is in San Francisco or New York, right? So that's what the green dots and blue dots represent, right? So the green dots represent houses in San Francisco, and the blue dots represents houses in New York, right? So that's the meaning of the color of the dots. And then you have this, this is one nice way to visualize. I mean, let's say you have 2 numbers you want to visualize. Let's say I give you height and weight of people in this room, right? What is one good way to visualize that, right? So let's say there are about 80 people in this room now. I write down 80 pairs of numbers, height and weight, right? So if you want to show one image which completely summarizes this entire data, what would be a good option? A scatter plot is a very natural option, right? So you would just, each dot would correspond to one of you, and you would just plot height, comma, weight. But instead of height, comma, weight, I also have height, weight, age, which latitude you are from, which longitude you are from. You have 7 numbers. Now, how would you visualize this? It's not so straightforward, right? Yes? Pardon? What plots? What? Yes. Good. Yeah. So that's a very good option, and that's what's actually happening here. So you've gotten the answer already. That's one of the ways. That's not the only way. That's not even the best way, or the one. There are other ways also, but this is one of the easier ways to understand, because scatter plots are, I mean, because humans and computers and screens are limited beings. We can only see 2D things. So what we do is we take pairs of all of these things. As you say, you have 7, right? So you can imagine all 7 choose 2 pairs, right? So you can take all 7 choose 2 pairs, and you can do scatter plot among any 2 of them. That's what you have here, right? So you have, let's say you have elevation and price, and elevation and square feet, elevation and something else, right? So you can take any 2 of the attributes, and then you can do a scatter plot of those 2, right? So that's what this particular thing. You don't need to really understand what this data is, but that's how this data is being visualized here. Right? Okay, fine. So that's the data. I've not told you what classification is yet. Okay? So classification typically is once you have data, and then you have what's called a label. In this case, you can imagine the label as whether it's San Francisco or New York. That's the label. Right? So the goal of a classification model is to classify an instance into either one class or the other class. Right? So in this case, let's say it's binary classification. We'll make it simple. So the goal of a classification model is it will take in these, let's say, 7 numbers, price, square feet, all that, and it will say, okay, I've looked at this house, and this house is most likely to be in San Francisco. So that's what is likely to be in New York. Right? So that's what a model would output. So the goal of classification algorithm is to use, let's say, data of these 1,000 houses, and to build a model like this, right? So the process of building or constructing a classification model is really the machine learning problem called classification, right? So classification algorithms are essentially those which take a data set like this and converts that into a model which takes in the input and outputs whether it's San Francisco or New York, right? So that's really what machine learning algorithms or classification algorithms are about. Okay, so this is okay, before we go into more complicated things, let's say you had only one number, right? So instead of 7 numbers per house, let's say you had only one number, right? Or let's say this particular, okay, so let's take houses itself so that it's easy. Let's say you had just only one number. What would be a natural way to classify, let's say, okay, before, I think that is what the next slide is. Let's say you have only one number, not 7 numbers, but just one number, okay, which is the elevation of the house. which height the house is built in. And this is how you've just drawn a line corresponding to the height that house is, right? So these are all, the blue lines are all New York houses, and green lines are all San Francisco houses, right? So you just had this one number, not 7 numbers. What is a natural thing that you would do, right? So now this is the data I've given you. Can you build me a classification model? Pardon? Okay, so let's say this is what, can you see this, right? So let's say this is the data available to you. What would be a model that you will tell? This is. Audios. Can you? Now it's fine. Yeah, so you were saying this is, let's say this is 240. Oh, I'm going close to the speaker, is it?
Yeah, that's why he puts.
Okay, got it. This number is 240 feet, right? So what are you saying? That is saying that if a house, so this is your classification model, that is if a house is greater than 240 feet, then it is green, otherwise it is blue. That's your model. That's a very good approximation. So that means that if a house really has, let's say, is 300 feet above the ground, then you will classify it as a house in San Francisco, which is green. Or if the house is less than 240 feet, you will classify it as New York. Right? So that's a good first cut model. But will this always work? Why? Because there are houses here also. Right? It is possible for a greenhouse to be at 100 feet also. Right? So that is that. So, but at least as a first cut is a very good thing. Right? So now that seems like the best that you can do with one feature. Right? Is that really? So now we can, instead of one thing that you have control over, instead of 240 feet, is there something better that you can do? You can do better here. We can go a little bit better. That way you will get this wrong, true, but you will get way more greenhouses correct. Right? So that's so you can choose this threshold. This is called a threshold. Right? So at what point do you threshold your feature and say everything above is one class, everything below is another class? So that is something which you can search over. Right? So how would you? What is this criteria for searching? Well, the simplest thing is. Right, let's do that first. Right. This is the histogram, right? I mean, that same data visualized in this form. Right? So just that blue and green are adjacent to each other. Now you can decide where to put your threshold, right? So you can put it in this point, which is 240 feet, in which case you would divide the data into two splits. In this side, you would have all green. In this side, you would have blue and green. That's the mix there. That means that if you just stopped here, you would be getting 63% of the houses correct. And so you would, that's better than random. Randomly, you would get only 50% correct, but you are getting better than random, which is a good point. But is that the best you can do? No. You can, the other extreme is you can go all the way down here and say every house that is above the sea level is a San Francisco house. You could say that. That means that you only get 56% correct. So you can either go this extreme or that extreme, or be somewhere in the middle, something like this, and say every house that's above 92 feet is San Francisco, and every house below 92 feet is New York. If you do that, you will get 105 plus 99 correct. Right? So you will get these 46 houses wrong. Right? So that you will get those wrong, but that's the best you can do with just, at least that seems to be a natural best thing you can do with if you had just access to elevation. Right? So now that's, you're already built a decision tree. Right? So this is already a decision tree, but it's the simplest kind where you have only one attribute. This is called an attribute or feature. One number is called, let's say, this elevation, or can be called a feature, attribute, other names also. Those are names for it. Right? So with just one attribute, you can build a thresholded tree which will give 82% correct, which is not bad at all. Right? So you can get 82% correct. But that's not the only thing you have. You have 7 numbers for a house, not one number. Right? Can you do better? Right? So this is really the core of decision tree, right? So you take one attribute and then you split based on that attribute, and then now you have these two other smaller data sets, and you can ask the question, okay, now I have built a decision tree based on one attribute. Can I do more? Can I do better? Right? So you can go ahead and recurse on this. Now you can essentially view this as the complete data. Now instead of totally how much did you had? 145, 201, about 300 houses you had in the first. But now that you have split the houses into two types, right? So one is houses that are elevation less than 92 feet and elevation greater than 92 feet. Once you have built that, you can essentially treat these as separate data sets already, right? So now you can ask the question, can I do more? Can I split these smaller data sets into even further purer things, right? So this is called, you ideally, what's the best case scenario? The best case scenario is you find one side has all green, other side has all blue, right? If you have that, that means that you have achieved 100%, right? So that's the best that you can hope for. So any blue in a majority green and any green in a majority blue circle is kind of not ideal, right? So that means that you are not getting the 100% accuracy that you might want. So that's called an impure split. So a pure split is something which is fully green or fully blue. Those are pure, right? So any green in a blue major blue data set and any blue in a major green data set is an impurity, right? So you can go ahead and keep on splitting this. How do you split this now? Well, you first split based on elevation, but there are 6 other attributes. You can go ahead and do that, right? So for this particular split, the left split, where the lesser elevation split, it's actually ideal to split based on price per square feet. Right? So if you did that, you can split based on some price per square feet. I don't know if you can see this well, and that will, right? So now you have 4. So for the lesser elevation data set split, you split based on price per square feet. For the greater elevation thing, you can split based on price, right? So if you did that, now you end up with every time you grow the tree, this is called growing a tree, right? So you start off with the root. The root node was, you chose elevation, and then you have to choose the split as 92 feet or some number. You have to decide that. And then once you've split that, you've gotten 2 data sets, and then you have to further choose some other attribute, and then choose some other threshold and keep on doing that, right? So at this is called a node of a decision tree, right? So this, each histogram here corresponds to what's called a node of a decision tree. At the beginning, you have only the root, which contains all the data set, right? But every time you go deeper, you work on a smaller data set. Why is that? Because the left node here only has houses whose elevation is less than 92. This part here only has houses whose elevation is greater than 92. So it's a smaller data set. And then you can split again based on that. So at each node, you have 2 decisions to make. What are those 2 decisions? Right? I mean, when you are building the decision tree, what all represent the decisions? Let's say you have built this. What all are things that you have to decide at the root node? Pardon? Yeah, no. At the root node, what would you said 92 feet, right? So, but there is one other thing. I said that if you had only one attribute, but you don't have that, you have 7 attributes. You have to choose which attribute first, right? At the root node, you have to decide which attribute you are going to split on and what is the value you are going to split on. You have to decide both these things. That's elevation, 92. That's the root node. And the left node is price per square feet, let's say $100, something like that, right? And the right side node is price, let's say $1 million, something like that, right? So that's each node is represented by, so the price, so each node is represented by an attribute, value, right? So attribute is what is the name of the attribute that you split on elevation or price or that, and then what is the value you split on, right? So that's how you build a decision tree. Each node, you will have to find out which attribute to split on, what is the value you have to split on. So how do you do that? Well, it's not really that difficult. You have 7 attributes. You can try all possible attributes, right? So elevation, I just gave you basically the answer. But really, how did you do that? You tried, you chose elevation because that was the thing which gave you 82% accuracy. Every other attribute would have given you less than 82%. Right? So if you had, first itself, if you had decided to split based on price, That might not have been very useful because both San Francisco and New York are very costly cities. So if you split based on price, that would not have been very useful, right? So you might find that at whatever price point you split, there are equal number of cheap homes and costly homes in both places. So that's not a very useful split. But elevation is arguably, at least in this data set, it seems to be a better way for using it as the first root node criteria. But once you've, that means that you can search over all possible attributes and all possible threshold points. You can do that, and that's how you build the first node. Once you've done the first node, building each of these other nodes is the same thing. There is nothing really different there. That's the same thing here. You once again search over to get, let's say, the left node here, you search over all attributes. Let's say price per square feet. Technically, you could search over elevation again, but it's not typically useful. You could do search over elevation again, right? So that's possible. Or let's search over all possible 7 attributes and all possible thresholds. This is not particularly hard because let's say you have a small data set of, let's say, 1,000 points. Potentially, there are 7 attributes, and each attribute can take, let's say, at most 1,000 values. So 7 into 1,000. 7,000 is not really a particularly hard, big number for a data set like this. So it means that constructing each node does not take too much time. So you can keep on doing this, and you can stop at whichever point that you want. You could have stopped at the root node itself, which is, you're saying that, okay, I've got an 82% accuracy, I'm happy with that. You can stop that. You could have done that, but that's not very satisfactory. Can you do better than that? So in this case, you could perhaps build one more level of the tree. That is, you could go one level deeper and say price per square feet and price. And you can stop here also, or you can go deeper. You can go on, you can keep on going deeper. And at some point, what will happen? Yes, so each of these circles will be all blue or all green. At that point, it makes no sense to split further, right? So if it's all blue or all green, what would you split it on, right? So it makes no sense. So that's, once you go there, you can stop. But you can stop before also, right? So you can say, well, I'm satisfied with my 90% accuracy, I'll stop. Or you can say, no, I want 100% accuracy, and you can go full way. So that's all is there to building a decision tree, right? So that's perhaps if you have not done a machine learning course, now you know already how to, your first machine learning algorithm, you can write it down. I mean, if you have all done a Python course, you can actually take a data set and use what I have said to write a code for taking a data set and building a decision tree. It's not particularly hard. You can do it right now, actually. That's all you need, right? Okay. So any questions on this? So I think this is a point where it's a safe point to stop and ask for questions. Okay. Yes? Yes. You can sit down. I can just speak up. Right. So as I told you, there are at each node, when you build to build a node, you need the attribute and what value you are splitting the attribute on. So you need to find both of these things. So you search over all possible values, right? In this case, it's a 7-dimensional, 7-attribute data set. So you search for all possible attributes and all possible values to split it on, right? So you do both. Right? So that's the best possible. So yeah, in a way, I'm guessing what you're asking is you are doing it in a node-wise greedy fashion, right? So what you're doing is that every time you split the node based on just the greedy, right now, what is the best thing to do? You don't split the root node based on what is going to happen here. You can't do that because that's a hard problem. You completely give up on that. At every node, you just decide to build the node which has the best accuracy for that particular node. That's it. Nothing more, nothing less. I don't know how it's happening. Fine. Yeah. Any other questions? Yes. Yes, at least when you build a decision tree, it matters. It matters, right? So, for example, that's the reason why did you choose elevation first, right? So, if you had, okay, sorry. Let's say you stopped here, right? So, let's say you've stopped here, and this is what you are returning. This is the classifier model that you are returning to the user, right? So, what will the user do? Well, you want to implement this user on this model in a new house. Some new house comes in. You have these 7 numbers. You obviously don't know what city it's from. You don't know whether it's from San Francisco or New York. What would you do? You would first check whether that house has elevation greater than 90 feet or less than 90 feet. If it is greater than 90 feet, you will check its price. And if its price is greater than something, you will put it in this right bucket. And this right bucket corresponds to, this is a majorly green cluster. So you would label it as San Francisco. Right? Yes, but that's not the model you built. This model you built has, so let's say you wrote a program for this thing, right? What you write is, if elevation of x is greater than 92 and price of x is greater than, let's say, 100, then San Francisco. If elevation of x is greater than 92 and the price of x is less than, say, 100, you say this is New York. If elevation of x is less than 90 and the price per square feet is greater than, let's say, 10, then it is New York. If elevation is less than 90 and price per square feet is less than, let's say, 10, then it is San Francisco. That's the if-else program that you would write. Right? So which means that the order does matter. Yeah.
For each node, we will check the accuracy of all the attributes.
Yes. Yes, you're correct.
And we'll pick which has the highest
Yes.
accuracy, we'll fit in there.
Yes.
Each node will do the same process.
Yes, each node will do the same process. So that's correct. So there are other ways of splitting the node, but this is one of the easiest ways. There are other ways to split based on things like entropy, Gini coefficient and all that. But accuracy is the easiest thing to explain. That's what I'm using. So when you are probably doing a proper machine learning course, you might see that this splitting is not done based on accuracy, but rather based on something else. But that's a detail and not the major message that's being sent to you. Any other questions? Okay. So I told you that you can stop here itself instead of going all the way if you keep on going, you will get a pure cluster. That means that you will get 100% accuracy. Why would you not always do that? Why would it make sense to stop here itself? Okay, so a lot of you have already done a machine learning course, it seems. So people who have not done a machine learning course, can you tell me what is a potential issue with that? Okay. Why not? Okay, that's a good point. Overfitting is the answer. There are two answers really. One is basically if you, let's say you are writing a program for doing this. To implement this, you just need 4 if-else. You need just 4 if conditions. But to do this, to go, let's say, one level deeper, you would need 8 if-else conditions. Right? So that is something which to keep in mind. It's not that big of an issue, but that's something to keep in mind. The bigger issue is that you don't really care about accuracy on the training set. Right? So that's whatever you have now is just the database that you have now. It's just the current houses. That's not what is the purpose of building this model. The purpose of building this model is to classify future houses, not the current data set. The current data set you can get 100% accuracy just by looking at the column. You already have the data. You already have the details of whether this house is in San Francisco or New York. So the goal is not to do well on the current data set, which is called, let's say, it's called the training data set. That's not the goal. The goal is to do well on the future data set, which is often called the testing data set. So by trying to do too much, let's say for example, you have the past year question papers of, let's say, MLF, right? So you go ahead and just prepare those questions. You don't read the content, you don't read anything, you just know the answers for last year's question paper for MLF. You will do okay really well, right? But you will not be able to answer any of the new questions, right? So you will not be able to get 100. Just because you got 100% on the past year question paper does not mean that you will get 100% in this year question paper, right? So that means that there is something you need to generalize also, right? So you need to get the principles and then go ahead and so that way you are more likely to do better on the future data set. The goal of studying is not to do well on the last year question paper, right? So that anyone can do because you already know the answer to it. The goal is to do well on this year's question paper, right? So that's the test data. So that means that it is not always optimal to, let's say, get 100% accuracy on the training data, especially because there might be one, let's say, anomalous house. Let's say there is one house, let's say you don't capture the closeness of a house to a sewer, right? So that's not one of the features, right? That means that you might have a house which is huge, which has everything, but it's like ridiculously cheap. Right? So by trying to build a model which does well on that particular house, you might say that, okay, if a house is large, very large and very cheap, then it is likely to be in New York. Let's say you build something like that, because you have not captured the fact that that house is close to a sewer, right? So then when someone else gives a new house, you might think that, okay, this house is large and cheap, so it's going to be in New York. So that is not really a thing that's happening. That's because you have just caught on to a pattern which is just nice, right? So there is, if you have any amount of data, you will always, the key idea is to distinguish between pattern and noise, right? So what is pattern, what is noise? So if you look deeply into everything you can, let's say I randomly put some blue and red dots on the board, right? If you look deeply in it, you can see any pattern, right? So, I mean, you can say, oh, that's really basically what you can look at the star and someone has drawn shapes of like the zodiac animals. But really, you could have drawn anything, right? So you could have drawn a picture of a unicorn fighting a bear if you want, right? So you could have done anything. But some people have, so that means that you can see pattern in everything. So the core idea of machine learning itself is to distinguish what is pattern and what is noise. Right? So if you try to overfit, this is what's called overfitting, that if you try to get 100% accuracy, that means that you are trying to see pattern in noise. Right? So you are seeing noise and considering that as pattern. Right? So that means that it is sometimes not optimal, even in terms of accuracy, to go all the way and build a 100% accurate on the training data classifier, right? Because that's not the goal anyway. So that's not what you are being tested on. You are being tested on the current year question paper and not the last year question paper. It is a good thing, obviously, to do well on the last year question paper, but that's not the goal. The goal is to do well on this year's question paper. Okay, so that's really the concept of overfitting in a nutshell. Right? So let's say you built this decision tree, which is you went all the way and you built a pure thing. But that's not really the goal. The goal is to do well on the test data. So if you with a pure thing and you try to make predictions on the training data, you will get 100%. Right? Why is that? Because you kept on building the tree until it became pure. Right? But that's not really the goal. The goal is to do well on the test data. So if you do that, you will get only about 89% accuracy, which is not bad. Right? So 90% accuracy on the test data is not bad, but it's not 100%. So that means that there is a difference between train accuracy and test accuracy. All right. Okay. Any questions now? Yes. 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 So there are two phases, right? So one is the training phase where you find what to do. Once you have found what to do, you write that down as a frozen thing, right? So that's I think you are probably confusing the training phase and the testing phase. There are two phases in which you build a model. The first phase, you build the decision tree. The second phase, you use the decision tree. There is a difference between the two. Right? So when you use the decision tree, you just write down a static piece of code. Like something like if elevation greater than 91 and the price greater than 100, then it is New York. If elevation greater than 91 and the price less than something, it is San Francisco. That's a static thing. There is no data or machine learning going on there. All the data and all the learning came in writing the code. Right? So that is, why did you use elevation first? Why did you use 92? Why did you use price next? Why did you use 100 there? That information came from the data. But once that information is extracted, the data is useless. Right? So once you have built the decision tree, I can throw away the data. Right? Because now I've built a decision tree, now I can throw away the data. When someone comes with a new house the next year and says, okay, is this house in San Francisco or New York, you would just use that static thing and say whether this house was in San Francisco or New York. The data is no longer used now. So once the data is useful for constructing the model, which is a decision tree, and once that is done, you can throw away the data. It has no use. Yeah. Any other questions?
So do we fix the threshold or the machine fixes the threshold?
Well, you write the program, so that means that you fix the machine. You write, as I told you, you search over all possible attributes and all possible values. Okay, so it means that you have, let's say, 7 attributes, and let's say, well, you can technically discretize the thing. You don't need to, let's say, you don't really care about $1 increments of price. Maybe you only care about, let's say, $100 increments of price. So you can discretize it and make it more reasonable. That way you can reduce the computational effort, right? So how much effort does it take? How much computational effort does it take to build one single node? That's something which you can reduce by discretizing the range. Right? So that's something. Yeah. Any other questions? Okay. All right. So with this, you've actually learned the first machine learning classification model, classification algorithm that. So this is a pretty quick summary of one of the classic algorithms. Okay, so now we are ready to move on to the next part of the workshop. So feel free to stop me and ask me for questions now, because we are going to move to something else. Okay, great. Right. So what does ensemble mean, right? So ensemble is, I think, a French word. So it is obviously an English word, but its root is in French, which essentially corresponds to multiple or together, or it's the same root as sample, right? So it's a multiple thing. I'm not really a etymology guy, so but the word, the way people pronounce ensemble, I was guessing it is French, and I'm moving with it, right? So it's not ensemble, but ensemble. Right? So French has different pronunciations. It's weird. Fine, but what is it, right? So it really is about combining multiple models, right? You have, why would that be useful? Let's say, for example, you have built one decision tree, right? But now your company, let's say you are a part of some company, and that company has decided to merge with some other company, right? So the other company has also, let's say, built a decision tree, right? And let's say it's also, each branch of your company has built a different decision tree, right? And now you realize you have each one of you are using one different model. All of those models are good, right? So there's nothing inherently bad about each of those models. Let's say you have a company which has, let's say, 100 branches, and each branch is unaware of what the other branch is doing. They are kind of replicating the work, and now the management has found out that, okay, you guys are all doing the same work, right? Now, what would be a natural thing to do? Let's say all of you are building decision trees to distinguish San Francisco from New York houses. I don't know why you are doing that, but let's say you're doing that. Right? Let's say you're doing that, and there are 100 branches of this house, and then of this company, and now the CEO has decided, okay, now you are building 100 models. Why are you doing that? Build a single model. Right? So you want, because all of you are the same, why are you doing that? Build a single model. What would be a natural thing to do? Well, of course, you can take it and train from scratch again, but what's a natural thing to do? Let's say you don't want to do that. That's too much effort. Let's say you have a manager there who is responsible for doing this job, and the manager has written an email to all of the 100 branches saying, please send your decision tree model, and he has gotten 100 emails from it. Right? What's a natural thing for the manager to do? One by one. So what did he say? Okay, that's one option. Any other options?
Take each model as a module and make another decision.
Okay, that's a very interesting strategy. Okay, great. Pardon? Yeah, great. That's the simplest thing to do, right? So what both of you are saying, what you're saying is that use one model and ignore the others, which is okay, but it is potentially possible that each model is good in a different area. It makes sense to not ignore them, right? So that's one good strategy, but that wastes a lot of things. What you are saying is a pretty sophisticated idea. It might have meaning, but it's a pretty complex. Let's not go there, right? What you're saying is the most natural thing, right? So you can view each model as voting for either San Francisco or New York, right? So let's say you get a new house data. You send it to all the 100 models, right? So which means that each model will say San Francisco or New York, right? So let's say you take a house and you send it through all the 100 models. Let's say 70 of those models say it's San Francisco and 30 of them say it's New York. What's a natural thing to do? Let's say you take San Francisco. You take a majority vote and do that. So that's the essence of, this is the simplest thing you can do. And it's a very powerful tool. And let me tell you, all practical models are like this, right? So they are messy, and let's say you join Google or Microsoft or anything like that, you will not be building a single model ever, right? So you will always be combining models in so many ways, and average is a surprisingly hard baseline to beat, right? So voting and majority voting and average and all that, that's a surprisingly hard baseline to beat. You can beat it by something clever, by like 1 or 2 percentages, but typically it's not even worth the effort, right? So you just average so many good models, so many reasonably good models, and you get a super powered model, right? So that's essentially the power of democracy at work here, right? So that's right. So that's the idea here. Real world machine learning problems rarely have a unique and single best solutions. So multiple thought processes and teams and approaches often yield equally valid but completely different solutions, right? So which means that you need to combine these solutions into one thing. So is ensemble methods, right? So you could say, okay, is that all it is? I mean, taking majority vote is like a fancy French name for majority voting. Well, it's particularly not surprising because democracy has lots of roots in France also. So that's, well, there is more sophistication than that, but at its core, it's that if you take away only one thing, saying that, well, if I combine several models and take majority vote, that's ensemble methods, you would not be very wrong. There are some sophistications to be built on top of this, but at its core, it's just that. You combine several models, take majority vote or average, and that's all it is, right? Okay, so here is one example, practical example. So this is kind of an outdated example because at this time, I think this was 2010s, 2008, 2007 timelines, where at that time Netflix was still a company which sent out CDs to the people of containing movies and not a VOD platform. There they had this challenge which had about 100 million star ratings of about 500,000 users of about 18,000 movies. Right? So at that time, this was considered a huge data set. Right? So this was considered a huge data set. And what it gave us, Netflix was using inbuilt, it was using its own recommendation system. That is, okay, now that it had this and it had a way for predicting another user came in. Let's say Netflix had access to, let's say, a new user or an existing user and a new movie or something like that. It would predict, okay, this user has liked, or it would build a model saying that this user is likely to give 4 stars to Lord of the Rings, so let me recommend that to him. So among all the movies that are there in my catalog, this user is likely to rate Lord of the Rings as the highest, so I'm going to recommend this movie to him so that he will buy that movie from me so that I can make more money, right? So that means that the recommendation system was core business driving proposition for Netflix. Even now it's the case, right? Most of you, let's say you are logging into Netflix or Amazon Prime or something like that, most of the time you will find that there is, let's say you watched something of your own, you'll find that the top row of recommended things is often useful and relevant to you, right? So, something which interests you because they have built good recommendation systems. So recommendation systems are a very important part of companies like Netflix, and they already had a system, right? So they said that, okay, we already have a system and we get about an average, we can predict star ratings to within about 1.5 stars, right? So if you can use this data and build another model for us, which can get a star rating error of less than 1.2 stars, which is something like a 10% improvement, then we will give you $1 million. So that was the challenge that came out. It was a Netflix challenge. And this was the data was very simple. It says it has just a list of things, a user ID, a movie ID, and the date at which they rated the movie, and how many star ratings did they give that movie. So there is just a bunch of data set like that. So that was about 100 million numbers like this, that's it. And the grand prize was to be given $1 million to the team which beat the Netflix writing prediction itself by 10%. That was the challenge. And what happened was something interesting, which not the Netflix solution itself, but rather what happened, right? So what happened was there was a leaderboard of sorts, and a lot of people quickly got to about 7% or so better than the system. So at that point, what happened was something strange, which was the leaderboard started reducing, the sense that teams 1, 2, and 3, they started forming a mega team. Right? So that means that this bell course pragmatic chaos was essentially a merger of several teams, right? So this is a Bell Labs team, and then there was a team from Yahoo by Yehuda Karen, and then there was a team from several universities. They all individually had teams which were performing, let's say, 6%, 7% better. And immediately, now that they realized that there was $1 million at stake, they decided, okay, instead of getting $0, I might as well get half of $1 million, right? So they all combined, and finally, the final team actually combined a total of 107 separate prediction models, right? So this is how naturally ensemble methods are created, right? I mean, because now you have a team of really smart people, each of them have built models. It's not easy to do something sophisticated with that, right? So you can't say, okay, now that I have a new team, I'm going to build something from scratch. It's much easier to take what you already have and combine that. And that's what they did. They combined a total of 107 separate prediction models to get the model which beat the Netflix by 10%, and they got $1 million. So the second team, so there was a lot of controversy around this event. You can go and read it. So the second team, which also beat 10%, but by like just an hour late or something, they also merged a lot of teams. So essentially, you can imagine let's say the unmerged list was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and suddenly 1, 3, 7, and 8, 9, they merged, and then the 2, 4, and 6 realized and they also merged, and like there was a merging challenge of sorts that was going on. Whoever got 10% above is going to get $1 million. So it was a challenge to get to that. Of course, you can say, what if everyone merged? Yeah, obviously they will beat, but then the denominator is going to increase, right? So you don't need to get 15% above Netflix. You only need to get 10% above Netflix. The moment you get that, the challenge stops, right? So that means that it makes sense to not merge too many. Well, in the real world, obviously Netflix would probably want to merge everything. But from the perspective of the contestants, you need to add as little as people as possible to get the 10% so that your denominator is small, right? So that's what they did. And each method uses a different approach. There are several things that you can use for recommender systems like factor models, regression models, neighborhood models, and so on. I mean, we'll not look at what these are, but all of these are based on different ideas of how people rate movies, right? So they're based on different assumptions, right? So people, one thing can say, well, people like movies based on attributes, right? That is, they have a favorite director, they have a favorite genre, they have something like that, and that's how they rate movies. Some people say, okay, that's not the case. People who have liked similar movies in the past, will like similar movies again, that's it. So that's, you can have things like that. You can have several kinds of models, and there is nothing intrinsically wrong with any of those models. Every model makes some assumptions, but every assumptions, there is error or issues with that. And by combining, you take advantage of everything, right? So that's what happened, right? So what the take-home message is that individual methods are never going to be used in practice. If it's something like Google is using, something Microsoft is using in practice, you can be sure that it is an ensemble method. That is, multiple models are being combined to create one mega model. Yes?
How do we combine those models?
There are several ways. The simplest is just majority voting or average. That's the simplest thing you can do, right? So you have 10 models, let's say. Model 1 is predicting you will like, your rating for Lord of the Rings is 4 stars. Model 2 is saying your rating for Lord of the Rings is 3.8 stars. Model 3 is saying it is 4.2 stars. Something else is saying you're 5 stars, right? So what would I predict? Well, average all of that and give that. And so that's the simplest way. There are slightly more sophisticated ways for doing that. Well, almost all of them correspond to something like a weighted combination, right? So, well, instead of averaging, I'll give more weightage to the model which does well on the Indian population, and I'll give less weightage to the model which does well on the European population, something like that, right? So you can have different weights for each model and say that, okay, they have 4 models, but the model which does well on the Indian population predicts you will get 4.2 stars. The model that does well on the European says you'll get only 3 stars. So I'm not going to say 4.2 plus 3 by 2, but rather 0.8 into 4.2 plus 0.2 into 3.0 and give that's your prediction. So you can combine models in a weighted combination. So that's the most straightforward way to do things. Yes. All right. So there are 2 paradigms of ensemble methods which are parallel and sequential ensembles. So what I told you is a classic example of a parallel ensemble. That is, each model in the ensemble is built independently, right? So when let's say the Yehuda Koren's team built the model, they were not aware of the Bell Labs model, right? So you had, let's say, this Bellcore team, right? So Yehuda Koren is the second team, core. So when the Yehuda Koren's team built the model, they were not aware of even what the Bell Labs team are doing because they were rival teams, right? So each model is built independently without awareness of the other model. And so that's why that's called a parallel ensemble. Each model is independently built, and then you combine all of them together and to get a single model. That's a parallel ensemble. And the classic example of such a model is bagging, right? So bagging is the simplest thing that you can think of. What I told you right now, you take several models and average them. So that's bagging. So there is the other kind of ensemble method, which is called a sequential ensemble, right? So it's a little bit more sophisticated, where when you build the first model you build, when you build a second model, you are aware of the first model, right? So you say, okay, my first model did well on the Indian population, but not so well on the European population. So when I build my second model, it should be the other way around. It should do well on the European population, and it doesn't matter as much if it doesn't do well on the Indian population, right? So you can, when you build a second model, you can be aware of what the weaknesses of the first model are and patch up for that. And you build a 10th model, you are aware of what the weaknesses of the first 9 models are, and you build up for it. So that means that I can't immediately say build me the 10th model. You can't do that. So that means that to build the 10th model, you need access to the first 9 models. models. So that's a sequential ensemble, right? And the classic example for that is what's called boosting, right? So that's the two main paradigms of ensemble methods. You can technically mix those two, but those are the two pure paradigms, right? So any questions on what happened? Yeah, any questions? Yes.
Is there a case where the average of the value, right? Its accuracy is lesser than the individual algorithm?
Okay, it's a very good question. Yes, you can construct that, but in most situations, that will not be the case. Yes. In most situations, if each of the models are built reasonably well, averaging will almost always get you a better answer. It is possible that it will not improve much, but it will not get worse. Any other questions? Yes. Right. So let's take the star rating model itself, right? Let's say you built a star rating model for the entire world, right? And then that you build the first model. It's a simple model, and then you realize, then you do some analysis of it and find that it has done well on the Indian population, but not so well on the European population, let's say. When you build, let's say you have decided to use an ensemble method. When you build a second model, would you keep doing the same thing? That is, what you can do is you can when you build a second model, you can increase the weightage of the European population and reduce the weightage of the Indian population, so that your second model is forced to do much better on the European population than the Indian population. So that means that now, by combining these two models, you have the best of both worlds, right? So you will do well on both the European population as well as the Indian population. So that's the goal here when combining, when you build these models. Yes.
So those two models are correlated.
Yes. In a way, negatively correlated, right? So it's so negatively correlated is still correlated. Yeah. So that's the idea. Yes. Yeah. Yeah. Well, it depends on what you call pre-us, right? So, what's happening here? Yeah. That depends on what is given to you. Let's say in the case of the manager combining branch things, you can view it as from the manager's perspective. Each branch's model was pre-trained. He doesn't care about it, and he's just combining it. So that's one way to look at it. But from the organization's perspective as a whole, it doesn't matter that the manager considers it as that pre-training and combining. But from the organization structure as a whole, they did build all the 100 models, and they trained the 100 models and then combined it. So it depends on who is doing the combining, who is doing the training, right? So that's. Yes. 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 Yeah, that's why I said that. Right? So sequential ensembles are much more complicated, right? So parallel ensembles are very easy, right? So I mean, it doesn't matter. You build each model is built independently and then you combine it. Sequential ensembles are a little bit more intricate. We will, if we have time, we'll probably look at that. So the data is being used. That is one standard way to do that is you increase the weightage. You are using the training data. So what you can do is you will increase the weightage of the population on which your first model is doing badly in, and you will reduce the weightage of the points for which your current model is doing well in. So that the new model that you are building is forced to do well and make up for the weaknesses of the previous models. So that's the idea. Yes.
It is more like active learning.
Let's not go there. So active learning is different. Where the label is not available to you at all, right? So active learning is different. Let's not go there. Yeah, you can do that, right? So I'm sure machine learning is being used in all financial markets, but not as much as you think, right? Because financial markets are extremely noisy. So the signal is very weak in most of those things. So you would guess that all the the biggest, the most successful markets are essentially those which invest and not trade, right? So investing is just saying that, well, humans are going to keep getting better. That's all that you need. Trading is, it's, because by definition, if there is signal, someone else is going to exploit it and it will become noise, right? So you can do that. I'm sure people are doing that. I'm sure if you go to an investment bank, these will be there, but these will not be the major components. So machine learning and boosting ensemble methods, they will not be the major components. They will be using this in addition to other classic techniques for doing this. Yes, but they can do that. Yeah, can do that. Yes.
So will we be using transfer learning when we take in the transformer methods?
Okay, once again, transfer learning is a different thing altogether. That is, the transfer learning is designed to ensure that your model works on test data which is different from trained data. Right? That is not the goal here at all, right? So the goal is still to do well on all data, right? So the goal, there is no difference between train and test data as of now. So there is train and test data are still the same. So transfer learning comes from, let's say you train a model for doing well on, let's say, European faces, and then you use the same model for doing well on Indian faces. That requires a transfer. That's the application of transfer learning. But as of now, that's not the goal. There is train and test data are still the same. Right? So it's not transfer learning. Yeah. Any other questions? Okay, great. So where are we on time? So it's 3 o'clock. What I'll do is I'll quickly go over parallel ensembles and move to sequential ensembles, because sequential ensembles, I have made prettier pictures, so I want to just show it off. That's it. Right. Okay. So let's look at parallel ensembles. Bagging, right? So bagging is simply averaging, I told you. But how do you build the individual models, and what are the conditions under which bagging will work, right? So you asked that, is it possible that bagging might hurt you, right? What you can show is bagging will never hurt you, but when will it most help you? That's the question you should ask, right? So averaging multiple models will almost always never hurt me, almost always not hurt you, but there are situations where it will not help you much, right? So what is the situation under which it will help you the most? So that's the thing that you will see. The situation is that each of the individual models are essentially learners which have high capacity and overfitting models, right? So if each of the models that you build, let's say, are decision trees that you build till 100% accuracy, right? So in that case, you will overfit it, and they are very high capacity. What do we mean by high capacity? High capacity means that give any data, it can learn to 100% accuracy. On the training data, obviously. Not testing data, it cannot guarantee anything. But if you give any data, it will learn a model which will have 100% accuracy on the trained data, right? So an example is decision trees, you keep on running it, you will get 100% accuracy. So that's an example of a high capacity learner. And so high capacity learners generally overfit, right? So that's the situation. Now you have multiple such models which are all overfit on potentially different training data, right? So they are not the same training data. But like I told you, you have 100 branches. Each branch has access to its own houses, right? Its own set of houses. Each branch 1 has built a San Francisco versus New York classifier on houses that it has. Branch 2 has built a San Francisco versus New York classifier on houses it has, right? So it's still the same distribution. It's still the same the patterns are still the same, but just that the data points are different, right? So that means that you have 100 models. Each model is overfitting on its training data, or something like that, right? So that means that you have a situation where general learners are going to overfit in high capacity. In such situations is when bagging shines, right? So to have maximum advantage of bagging, you must have models which are individually very different, right? And that will happen if you have each learners are high capacity and generally overfit. So completely skip this part, which is I've talked about regularization, which is something which you will see later. So what does bagging do? Bagging simply combines several separate models learned on some subset of the data. Why am I saying subset is I can take the full data as the data of all houses, right? No single branch has access to that, right? So a single branch might have access to only some houses, right? So that means that each model is trained on a separate, different subset of the data, right? So that's the idea here. You have combined several separate models learned on some subset of the data, and then you simply average all those models. So average makes sense for regression, majority vote makes sense for classification. So that's the idea here. So the key insight, why does bagging work, right? So why does bagging not fail is something you can show mathematically, but why does bagging, so not failing is not the same as succeeding, right? So not failing simply says that you've met the bare minimum, right? That is your ROI is 1, right? So if your ROI is 1, return on investment is 1, you have not failed, right? So to succeed, however, you need an ROI of greater than 1, right? So that's the idea here. So the key insight is when you have these 100 models, let's say, are each of them are very different, right? So let's say you have the let's say all of these 100 models are good in some sense, right? So that is, they all do reasonably well, but they are very, very different. Let's say one model is a decision tree where the root node is elevation. There is another model whose root node is, let's say, price. There are different models. They are very, very different. By combining them, what you get is essentially, you can essentially average out the noise. So that's the effect that you get. By averaging out the noise, which is, because they are different, each model has different noise. Right? So if you have 100 models, they are all the same, let's say. Right? Averaging will give you nothing. If you average 2 models which are looking very, very much the same, the average will also be the same thing. There will be no advantage. So you will get an advantage only when the 2 models or the 100 models that you are averaging over are all very different. Right? So that's the idea here. And in such situations, bagging, which is essentially averaging or majority voting, will have a much better performance than any individual model there. Let's skip this part. Let's skip this part also. So ignore all that. So this part is simply saying that the mean squared error of bagged model is no worse than the average mean squared error of the individual model. So this is what it means when I said that the bagged model will not fail, right? So this part says that the mean squared error is no worse than the, that's true. But when will it succeed? When it will succeed, by that I mean that the mean squared error of the bagged model is much lesser than the average mean squared error of each of the individual models, when the variance of these models is much larger than 0. What do I mean by variance? Let's say I have 100 models, and that means that for any given house, these 100 models don't agree. They all predict different things. Right? If that's the case, that means that the variance is high. Right? So under such situations, your bagged model will do much better than any individual model. Right? So that's the idea here. So don't worry about the math part of it. The only thing that you need to take home is just these 2 messages. That's the mean squared error of the bagged model is no worse than the average MSE of the individual model. And when will it be much lesser? It will be much lesser when the individual models are all very different. Right? That's all that you need to take home. So any questions on these 2 messages? Right. So now I am going to tell you that decision trees are a very good candidate for bagging. Right? So they are very easy to overfit and they are very difficult to regularize. I have not told you what regularization is. But so it's a highly unstable learner. What do I mean by that? Right? Let's say I just change the data set a little bit. I ask you to construct a decision tree with, let's say, 1,000 points. Right? Let's say I just remove 100 points and then ask you to construct a decision tree. The decision tree that you would return with these 900 points is going to be very different than the decision tree that you would return to me with 1,000 points. So that means that the decision tree is very sensitive to data. Right? So if you change the data a little bit, the final model that you are going to return can be very different. So it's a very unstable learner. Right? It's a good learner, but it's still an unstable thing. Right? So that means that bagged decision trees by themselves are very powerful. Right? So how would you go about doing that? Well, let's say right now you're not combining 100 models. That is, you're not working with pre-trained models, so to speak. Now you want to train bagged models from scratch. How do you do that? Now you have 100 branches. Each branch has, let's say, 1,000 data points, right? So now you've combined all that and built one data set of 100,000 points. Now what you can do is, you can train 100 models again on several subsets of the data, right? So now you have 100,000 points, and you can, say, train model 1 with the first 50,000 points. You can train model 2 with another 50,000 points. You can choose randomly 50,000. You can toss a coin for each of the points and then train a model separately. Now you will realize that there is an overlap in the data, right? So model 1 and model 2 can have overlapping data. That's fine still. That's the reason, that's the place where the fact that decision trees are highly unstable comes into play. Even if you change some data points, the decision tree is going to be very different. And you have every reason to think that all decision trees are reasonable. Why is that? Because all decision trees are still trained on some data, right? So they are not, it's not as if though someone has hacked in and wrote a random decision tree. All decision trees that you are training here are trained on some data, which means that all decision trees are reasonable, but all decision trees are trained on different subsets of the data, so they will be very different, right? So that means that, so bagged decision trees by themselves are very powerful, right? So by you train 100 decision trees, each decision tree is trained on a different subset of the data. These subsets can overlap, that's fine, but they are trained on different subsets. That alone is very powerful. But you can go one step further and make one of the most powerful classification algorithms known in practice, called the random forest, right? So you can go one step further and do that. But before we do that, let's see if anyone has any doubt on the bagged decision tree. So are there any doubts on the bagged decision tree? So do you understand how do you build a bagged decision tree? That is, you all know how to build a single decision tree that we have seen. How do you build a bagged decision tree? You just build multiple decision trees on different subsets of the data. That's it. That's a bagged decision tree. And then you average it or take a majority vote. That's your bagged decision tree. Okay. All right. Any questions on this? Okay. So if there are no questions, let's move. Okay, so what am I saying? But here, so they are themselves very powerful, but you can go one step further and make bagging a very powerful tool, right? So as I told you, one way to make bagging very powerful is to make these individual models have very high variance. And how would you go about doing that is this particular thing, right? So to increase the variance, what you can do is, when you construct a decision tree, what do? You search over all possible attributes. When you construct a decision tree, when you construct a single node of the decision tree, you search over all possible attributes and all possible thresholds, right? So which means that there is, you can make it even more random here by saying that when you are, let's say, building the right node of the root of a decision tree, you decide, okay, now you can't use all 7 attributes. You can only use price or elevation, or price elevation or price per square feet. So you randomly select some attributes to each node and say that, oh no, you can't use all of that. You can only use these 3. So if you do that, what do you gain? You seem to be losing something, right? So that means that you are not searching over all possible values that the node can take, which means that it is suboptimal. Yes, that is correct. But you also gain something. What do you gain? What you gain is, even with the same data, right? So forget different data. Even with the same data, when you build 2 different decision trees, you will have different decision trees. Why is that? Because if you have the same data, decision tree is a deterministic procedure, right? So I give you this data. How would you construct the decision tree? Well, you take the root node, you construct a root node by searching over all attributes, searching over all thresholds, and fixing them. And you keep ahead. And there is nothing. If I give the same data again, you will return to me the same decision tree. There is nothing changing there. But the moment I say that, okay, now each node, I'm going to make it random. Each node is not allowed to choose all attributes, but rather only a subset of the attributes. Then that means that even if I give the same data again to you, the decision tree that you will return to me will be different. Right? So what's an example? One example is, for example, the root node. Let's say if the root node was elevation, that we would have chosen. But now, when you construct a decision tree, I'm saying that, okay, the root node, you can't use elevation. You have to use either price per square feet, or let's say area or something like that. So those are you can't use elevation. Now that means that the decision tree that you are going to construct is by nature going to be very different, because the root node change means that this seems to be keeping on. The root node change means that the model is going to be very different, right? So that is a trick there. So technically, yes, you are losing out on a single decision tree. Any single decision tree that you construct with this is going to be weaker than the standard decision tree. Why is that? Because each node is less powerful than decision tree counterpart. But you can make up for that by having multiple decision trees and averaging them. So that's what a random forest does. So here is an algorithm, a pseudocode, so to speak. So you have 2 parameters, A and B. Right? So A represents the fraction of data that you take in each to construct each decision tree, and B represents the fraction of attributes that you take to construct each node of a decision tree. Right? So a typical A comma B can be 0.5. Right? So this is what you do. Let's say your goal is to construct 100 decision trees. Right? So that's your n s would be the 100. Then you would select A into m samples at random. Right? So let's say your m was 1000. You would select 500 samples at random. Right? And then you learn a decision tree with that sample. Right? So that's the second step. But here's the thing here. While constructing each node of the decision tree, instead of searching over all the D possible attributes, you only search over B into D possible attributes when you construct the node. Right? And you choose the best split only among those. So that's the other part. So and then you finally, you make the average, return the final random forest, you return it simply by averaging all the 100 decision trees. Right? So okay, before we go there, let's do a sanity check. What will happen if I set A equal to 1 and B equal to 1? There's only one decision tree. So if I set A equal to 1 and B equal to 1, that means that I am selecting all samples and I'm selecting all features. So what I will learn is just a single decision tree. Right? So yeah, I might learn 100 of them, but 100 of them are all the same. Right? So it's like I've learned one tree and it's a random forest made up of cloned trees. That's it. Right? So there is no difference, no variation. That's one X tree. Let's say A equal to A equal to 0.5 and B equal to 1. Then what does it correspond to? B equal to 1. What does B equal to 1 mean? So that means that each node, all attributes are being used. A equal to 0.5 means that to construct each tree, you are using only half the data. So this is exactly what a bagged decision tree is. So each decision tree is constructed using standard methods on some subset of the data. Right? So that's a bagged decision tree. But a typical value, on the other hand, would be A and B both about half. Right? So this is something which you have to choose. What is the right value of A and B? There is no universal answer, but 0.5 is a good point to start. Right? So typically, let's say you are building something for some data, you might start off with A 0.5, B 0.5, but then you can tweak around with. So you can try A equal to 0.6, B equal to 0.4 or something like that. You can keep on tweaking this. Let's say you are using Python to do this. These are all standard arguments that you can give to the decision tree construction. So this, I don't know what the names are, but you can give both of these as arguments to your Python decision tree constructor. Yeah. All right. So any questions on the random forest? Yes.
What if we keep the order of the attribute differently in each model? Order of the attribute.
What do you mean by order of the attribute?
Like sir told about the price. First pick the price. Then
Yes.
like that for each model it will be different.
So the order is not well. You don't decide the order. Each node is just constructed independently. So you can't choose. Order doesn't make sense. Right? So your order makes sense in a line. Right? So in a tree, order doesn't make sense. First of all, and secondly, you don't construct a tree as a whole. You construct one node at a time. You don't construct the entire tree. You construct one node at a time. So the only reasonable thing you can say is, when you construct that node, I don't consider all possible attributes. I'll only consider a subset of the attributes. That's exactly what random forest is. Yes. 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 Mm-hmm. So you see where the loop is, right? So to build the decision tree, you use the same samples, but within the decision tree, each node is a different set of attributes. So to build the decision, let's say you are building 100 decision trees, each decision tree has the same set of data points. Okay, so but within this thing, each node has a different set of attributes, right? So you can say, well, the root node can use only elevation, price, and price per square feet. The left node can use only price per square feet, and area. The right node can use only area and nearness to main road and something like that, right? So each node has a different random set of attributes it can choose from. But the tree as a whole uses the same set of data points. So but of course, the second tree will use a different set of data. Yeah. Yes. Any questions? Okay, great. So, so this is something which you will encounter in your data science career. This is the first thing you will try. Anyone gives you some classification task, the first thing you will try is new random forest and random forest.fit off. That's the first thing you will try. You will get a number, and you will spend the rest of the month trying to beat that. That's what will happen, right? So that's what and then finally you will realize you spent 1 month to beat the random forest classifier, which already got 80% accuracy, and to get 82% accuracy. Then you beat yourself. Was it worth 1 month to build something just 2% better, right? So that's going to be your, if you are going to be working in data science, that's going to be a major part. So that's why most people don't even bother with doing anything, but you can do better than random forest. I'm not saying that's the best, but to beat random forest requires a lot of effort. Random forest is zero effort, right? So it's already there. You can just say rfr.fitoff, rfr.classifyoff, you'll get something, you're done, right? So it's a very good baseline to have, and most of the time in practice, it's sufficient. So that's all we have. Okay. All right. Okay, so this I think we are, so here is one example of, let's say you have this data. I don't know if you can see there's a difference between train and test. So this is dark red and light red. I don't think you can see the difference, but that's here, right? So dark red and dark blue points are training points, and light red and light blue points are test points, right? So you have train and test points here. And if you train a decision tree on the train points, this is the decision tree that you would get. Right? The red corresponds to one class and blue corresponds to one class. And you would get 78% accuracy on the test data. Right? Of course, you will get 100% accuracy on the train data, but only 78% on the test data. So if you build a decision tree on the same, a random forest on the same data, you'd get 88% accuracy. So it's a very simple data. You can see it's not even very complicated, but even in such simple data, random forest shows its advantage. All right. Okay. So this is simple. Okay. Now we'll move to sequential ensembles. I don't think we have too much time. So what I'll do is I'll not show the math of it and just show the philosophy of it and move on. Okay. Any questions so far? Okay, so the classic paradigm for sequential ensembles, it's what's called the boosting. There are other frameworks also for sequential ensembling, but boosting is the classic paradigm. And what is the setting under which it works? Right? So we saw that the setting under which bagging works is that if each individual model is a powerful model and it can overfit, right? So in that situation, you have something to gain by bagging. So boosting is kind of almost the reverse of it. That is, what you have is each individual, you have the ability to build individual models which are only slightly better than random. Right? That's the question here, right? So your individual models are all weak, right? But they are better than random, but only slightly better than random. The question is, can you combine enough weak people into one strong person? And so that's the question here. So if you want, let's say, one pithy quote for doing this, what bagging does is it combines a lot of, let's say, strong but erratic people into one dependable strong person. What boosting does is it takes a lot of dependable but weak people into a dependable strong person. So that's one way to look at it. Don't quote me on this because I just came up with this quote on my own, but that's one way for you to remember what's the difference between bagging and boosting. So that's the thing here. Each of these people can do better than random, but they are very stable, but they are only slightly better than random. Right? So how do you combine several such people, several such learners or several such models into one strong model? So that's the question. Right? So this is the thing here. You have access to a learner that gives a classifier fitting the trained data, but it is weak. Right? So you can only do slightly better than random. Right? So in this case of binary classification, it can do, you give any data, you can get, let's say, 55% accuracy. That's, you have somehow a magical black box. What it says is, you give me any training data, I will guarantee that I will get 55% accuracy. Right? I'm not guaranteeing anything. I might get 100%, but I'm not guaranteeing you that. I'm guaranteeing you only 55%. Right? How would you, but the point is you can use me several times. So it says, okay, if you use me just once, I will guarantee 55%, but you can use me several times to somehow get whatever you want. That's the thing that you have access to. So is there a way to create multiple such weak classifiers and boost them? That's the boosting thing comes here, right? So you have multiple weak, dependable classifiers. You combine them and boost them into one stronger one. Right? So a parallel strategy will not be very successful here, right? So why is that? Because these learners are stable. That means that if you give them multiple things, they will all return the same thing. They will all be 55% accurate, and you average them, you'll get 55% accuracy, right? So it will not be much better than that. Because why is that? Because they are all the same model. So average multiple things, but the same thing, you will get the same thing. You will not get any advantage. So a parallel strategy will not be successful here. So each new week, so that means this is where a sequential idea comes in. You build models one by one. So each new weak classifier built must strategically cover for other classifiers' weakness, right? So let's say you're building the 10th classifier, it must cover for the weaknesses of the first 9 classifiers. Right? So that's the idea here. How would you go about doing that? The key idea is that the weak learners are given weighted training samples, right? So until now we have seen, let's say, decision trees or things like that, where the number of data points was really, all data points were created equal, right? So that's the situation when we do this. But here, what you do is you assign a weight or importance to each data point, right? So at the beginning, you give equal importance, but then when you construct, let's say, take the European Indian population kind of example I gave you, let's say, and when you begin, you give equal weightage to European and Indian population. You build a classifier, and you find that you've done well on Indian population, but not done well on European population. What you do is, it's not one extreme you can do is you can just give the European population. That's too extreme. What you do is, well, you reduce the weightage of the Indian population and increase the weightage of European population, and now you build a second model which can potentially make up for the weaknesses of the first model. So that's the real core idea here. So a weight of a sample depends on how the previous weak learners have done on that sample. So that's the core idea here. And once you have this idea, it's not particularly hard. You have an algorithm here. Don't worry if the algorithm is too complicated right now. So the only thing you need to be aware of is this is the gamma, right? So what is the gamma? The gamma is the guarantee that the weak learner gives you. It says that, okay, I can get you 55% accuracy. That's the guarantee, which means that gamma would be 0.05, right? So 0.55 is your guarantee, which means that the edge over random is 0.05. So you have a weak learner guarantee which says that I can get you an edge of gamma over random, right? So that's that. And then you have a beta which is, it's greater than 1. That's the only thing you need to know. This is going to be greater than 1, right? So 0.5 plus gamma by 0.5 minus gamma is going to be greater than 1. So what all this does is, essentially, you start off with equal weightage. So this is the initial importance of all the samples. Initially, when you begin, you have no reason to prefer one sample over the other, right? So in the initial case, you will give an equal importance to all the samples. That's why you get, this is a vector here. So you give an equal importance of 1 to every sample, right? So that's what you do. And then there is a loop here. You give your data, which is the same. The data is going to be the same, but the weights are going to change, right? So you give the data and the weight to the weak learner, right? The weak learner will take the data, weighted data, and it will return a classifier to you, right? Once you have the classifier, what you can do is you can check how well does this classifier perform on each data point. So that's your LTI, right? So HT of xi is the prediction of model T on data point xi. So what do you want? You ideally want HT of xi to be equal to yi. Right? So yi is either, let's say, +1 or -1. This is your data. You have xi, yi data. Each xi is some vector. It doesn't matter. Each yi is either +1 or -1. Right? So you ideally want, if your model T, HT, has performed well on data point xi, HT of xi will be equal to yi. Right? So which is, if yi is +1, HT of xi is +1. If yi is -1, HT of xi is -1. That's the best case scenario. But that's not going to always happen, right? So what you are, HT is only a weak learner. It's not a perfect learner. So there will be points where HT of xi and yi will be different. It is possible, for example, HT of xi to be equal to 1 when yi equal to -1, or other way around. So in either case, you can take the absolute value of the difference and divide by 2, right? So this LTI is going to be equal to 0 when model T predicts data point I correctly, and it's going to be equal to 1 if model T predicts data point I wrongly. So that's LTI. Now you use LTI to increase. So what would you do? Well, if LTI is 1, LTI is, okay, what should you do? If LTI is 1, you should increase the weight of data point I. Right? Why is that? Because your current model has predicted data point I wrongly, right? Which means that in the next model should somehow take care of it somehow. Which means that how would you do that? Well, you would increase the weightage of data point I. So that's what you do here. So WT plus 1I is going to be equal to WTI multiplied by beta power LTI. So power is simply to LTA is just 0 or 1. So you either keep the weight as it is or increase it by beta. So beta is greater than 1. So you would either you would increase the weightage of the ith point if it got classified wrongly, and you would keep it as it is if it got classified correctly. That's all this is saying. Right? And once you have got the new weights of all the data points, you go ahead and loop it again. And so you can keep on doing this, and the hope is that after let's say after any iteration, the weightage of the points which are classified wrongly will be very high, so that the next iteration will take care of it. So every iteration you will either, so that's the thing here. So there is this famous quote, right? So I don't know who made it. So every time I either win or learn something. So that's the thing here. Either you got that input correctly, or you learned that I am weak in that area, so I'm going to give more focus to that area. So either way you win. So it's a win-win situation. So that's the idea here. And finally, once you have all the models, you can combine all of that. So you just add all of that and take the sign. So that's equivalent to majority voting. Right? So you have plus minus means that adding and taking the sign is equal to majority voting. So that's the algorithm here. Don't worry if you don't get the symbols and math behind it. The core idea is pretty simple. That is, if you your current model predicts a given data point wrongly, the weightage of that data point should increase. That's the only thing that's happening here. Okay. So here is a illustration of it. So this is the data. And what is the weak learner? The weak learner is something very simple. That is, you can draw a horizontal or a vertical line, and one side is blue, other side is red. So that's the only thing that you are allowed to do. Right? So now, okay, now we have this data. Can someone draw a horizontal or a vertical line? What is the best horizontal or vertical line? You obviously can't get 100% accuracy with any horizontal or vertical line. So let me start off the answer first. So this is a good starting point. You draw this horizontal line and say that everything above is red, everything below is blue, right? So you started with this. Have you gotten 100% accuracy? No. So what are the points that you classified wrongly? These points, right? So what will happen to the weightage of all the points? The weightage of these points will increase. The weightage of the rest will stay the same, right? So you can see that these circles have gotten bigger, right? So is it visible? So these circles are bigger than the other circles. Is that clear? Right. So now we can run the data again. Now can you essentially, what does it mean to have bigger circles? You can essentially imagine the data point is repeating or something like that, right? So that's the idea here. Now can you think of a straight line which will get most of the weighted data correctly? Now if its weights should also be there, what would be a good answer? Horizontal line, but one step lower, right? So this you can do. So now, is this classifier getting 100% accuracy? No. What is it getting wrong? These blue things it's getting wrong. So you can do that again. So you end up getting this. So you can see that these points were classified correctly by both the weak learners. So these points were classified wrongly by one of the weak learners. Right? So now you can go ahead and do this again. Now if you do, what will happen? So this is again a little bit tough question. So the answer is, this is what it will do, right? So if you say what is the best weak learner now, so this is the weak learner, that's best. So does this classify everything accurately? No. So it doesn't classify these things correctly. So those things will increase in, doesn't classify these points correctly. So these points will increase in weight. This happens. Okay, now what do you think is the best classifier you can think of? Vertical line on the other end. So this is what you would do. Okay. And if you, let's say now you stop now. Let's say you stop at 4 iterations and say, okay, I've combined my 4 classifiers. This is what you would get. It's a pretty decent idea, right? So it is, you've gotten these points classified correctly. You've gotten these points classified correctly. This area seems to be a problem of, area problem. So this area seems to be problematic. Maybe you just have to run for more iterations. Let's do that. This is your weighted data 5, and you can keep on repeating. If you can, try both and take the best out of the two, right? So that's really the message that you will get from machine learning. If you are not sure, try both and choose the best. So that advice is going to stay with you throughout, right? So in a lot of situations, you're not going to get concrete answers because there are no universal answers. So the answer depends on the situation. Try both and take the best. Right. So you can actually prove that this algorithm works, the boosting algorithm works. I'm not going to do that because I don't think we have the time, and I'm guessing that you guys are already probably tired. But yeah, the algorithm, the idea is pretty simple, and the intuition is sensible. There are some issues with the algorithm. For example, you have to know beta, right? So that is, it's not reasonable to expect to know gamma. So gamma is the edge over random. How can you build classifiers, build algorithms that, let's say you know that these classifiers, the weak classifiers are better than random, but you don't know how much better than random. Right? In that case, how would you deal with that? There are ways to deal with that also. That leads you to the famous AdaBoost algorithm. So that you might have heard of. It's essentially the same as this, just that you don't know gamma. You don't know how much better than random each of the individual weak learners are, but you still want to run the algorithm. Because you can see that if you don't know gamma, you can't run this particular algorithm. Why is that? Because this algorithm uses beta. And beta is 0.5 plus gamma by 0.5 minus gamma. So you can't, if you don't know gamma, you can't run this algorithm at all. Right? So it's not possible. But there is a modification you can do which does not use gamma and in fact measures gamma and runs the algorithm. That is called the AdaBoost algorithm. I'm going to skip this. I'm just going to show you what it does. Essentially, it measures gamma and sets beta to be equal to 0.5 plus gamma t by 0.5 minus gamma t. So the one major difference is that it's not equal weightage anymore. Right? So previously you had equal weightage, right? So all models, you just added all models and then took a sign, which means that it is equal to majority voting. Right? In AdaBoost, that's not the case. So it's a weighted combination. And it's kind of sensible also. A model is weighted by how well it has done. Right? So you can say all models are better than random, but obviously a model which does 90% better should be given more weightage than something which does 60% better, right? So that's what this does. So beta t will be larger if a model has 90% accuracy. It will be smaller if it is only, let's say, 60% accuracy. That's the idea, which is sensible. And arguably this is one of the foundational algorithms for, I don't know if it's used as much in practice, but it's kind of like an ideal algorithm. That is, it's very useful for teaching, and historically it has a lot of significance. In practice, some variants of this are used, but not these algorithms exactly. So on the other hand, random forest is used as it is, right? So random forest, nothing fancy goes on, it's just that is used. AdaBoost by itself is not used as much. You can use it, there's nothing stopping you from using it, but there are slightly better algorithms, more complicated than this, which will do better. Right. But still, it's important to learn a simple algorithm before you go on to more complicated algorithms. Okay, great. Any questions? Okay, cool. If there are no questions, I don't think I'm going to do the proof. I was thinking maybe I will consider, but I don't think it adds any value to the session now. I'll just skip it. All right. So if there are no other questions, we can just wrap this session. You can ask any general. Okay, I think that would also be nice, right? So we can wrap up this particular session. Yeah. The slides for this. I think, yeah, I'll send you a link. It's already available on the web. I'll just send you the link. Yes. Yes. Yes.
I asked you about the active learning. You said
Yes.
we don't have language. Can you explain that?
Active learning is a slightly advanced concept. I don't think it fits in with the scope of this particular.
What is the difference between this thing and that?
Active learning means that you don't have access to labels at all, right? So that is, let's say you are trying to, you have access to X's, you don't have access to Y's at all, right? So you want to, it's an interactive algorithm. That is, you decide, okay, I want to know the label for this. You can go ahead and ask the human will say, okay, there will be no labeling per se, right? So let's say labeling is costly. Let's say, for example, your X's are all MRI images and YAs are saying whether this has cancer or not, right? Which means that to label a single MRI image, let's say a radiologist has to go through it for 1 hour, right? Which means that it's a costly process to label. So you can't give like 1 million images and ask a radiologist to label all 1 million images. They will label for you, they will cost you cost you a lot of money, right? So you can't do that. So it's important to be label efficient in that case. So what an active learning algorithm does is it only asks for a label if it thinks it will be useful. It will not ask the label for every data point, only data points for which it considers it to be a useful label. So that's an active learning algorithm.
Data sets are rare.
The labels are costly. Right? So you can get the label, but labels are costly. So you don't want to get all the labels. You only want to get the essential labels. Yes.
So what is meant by accuracy in a recommendation engine? Like for example, if it is a classification model, yes or no, we can somehow say that how much of it is accurate. But a recommendation engine, for example, if a new user is watching a movie, he has watched a movie, then you should recommend 10 new movies. Like how will you measure the accuracy? Like what is meant by accuracy in that?
Yeah.
manner?
There are several ways to do that. So the first is to reduce it to a regression thing, right? So let's say you don't do that a ranking problem at all. Just say, okay, how much stars would you have given to Spider-Man? How much stars would you have given to Lord of the Rings? How much stars would you have given to Avengers? Something like that, right? So and then you just make it how much your task is to just predict how much stars would a given person give to a given movie.
No, it's not about the stars. It's like basically it's like you want to recommend 10 new movies to the person who
Yes.
has watched.
Yes.
So like I don't want to give stars. He has to first watch the movie.
Yes.
So like what is the accuracy factor over it? So that
Right.
you said that 10% is like given an example.
Yes.
So what exactly are we measuring over there?
Right. So the Netflix thing was simply star ratings, right? So what they have done is they have asked star ratings from, let's say, 1 million star ratings, but they don't show all the star ratings. They only show 500,000 star ratings, and they ask you to build new things, and then so the star ratings are used to build a recommendation system. So recommendation, they are not directly asking you to evaluate the recommendation system, but rather they are asking. So if you have a perfect star rating system, prediction system, you obviously have a perfect recommendation system. But you can have a good recommendation system even without having a perfect star rating prediction. So for example, I don't need to know how many stars you would give to Lord of the Rings. If I know that you would rate Lord of the Rings more than Spider-Man, I would recommend that to you. I don't need to know the exact star rating. So that's called a ranking problem, right? So that's the exact problem that, let's say, search engines also face, right? So they don't care about, so there is the idea that there is a right answer. You might not know what the right answer is for the test data, but there is some right answer, which is a ranking of all the movies, right? So each person has the ranking of all the movies that they are likely to watch. You might not know it for some, let's say you have not used Netflix at all, and you suddenly, let's say, log in. Obviously Netflix would not know the answer, but the assumption is that there exists some answer, right? So that means that in your mind, there is a ranking of movies. Netflix does not know it, but there is such a ranking. So the goal is to do as well as possible and align the Netflix's movie ranking system should align as much as possible with the implicit hidden ranking that you have in your head. Right? So you could have a ranking of movies. If Netflix can figure out that, okay, you have watched these 3 movies, and people who have watched these 3 movies generally have this ranking as the best ranking, so I will predict the same ranking to you. Right? So that's the idea here. So you are right that evaluating rankings is much harder than evaluating things like star ratings or San Francisco versus New York. Those things are easy. So those are classification, regression. The question that you are asking is, how do you evaluate recommendation?
What kind of books is recommended?
Yes, so you could say one way that is you want to evaluate rankings. So you have a ranking in your mind, and there is a ranking that the company returns. How do you say that? Obviously it's not going to be right or wrong, right? So
That's the problem. Like you can use any algorithm to get any set of books, but you don't know if that set of books is the right answer or not. Like this is.
Okay, so when you evaluate it, the hope is that you have done an exercise. Let's say I've gathered the book rankings of the entire population, but I trained my model only on the first 2 columns, right? Let's say I do that. To evaluate the model, I will evaluate my model on these 3 columns, right? So which means that there is a right answer. just that the model is not aware of it before training. So after training, the hope is that that model figures out the right answer. Right? So what you are asking is a different question. The different question is that someone has not read the book at all, they might not even know they might not know the ranking. That's, I mean, even in their mind, in their head, they don't have a ranking.
No, like hypothetically, see, suppose like a books I take, okay?
Okay.
So suppose someone has read, fine, Harry Potter.
Okay.
Okay. So now I can use KNN for with
Okay.
user rating.
Okay.
I can use K-means using clustering, and both of them will give me different set of recommended books. Now, how do I know which algorithm is a better answer? Like,
Yeah, that's it, right? So you give both and then ask, I mean, let's say I give it to you, right?
how
So
do you exactly get an accuracy that this one will give you a higher accuracy? Because
it's subjective, right? It's subjective, right? So I would give both the ranking list. Let's say two algorithms give two rankings. I'll give one ranking to you and say, okay, what do you think about this ranking? You'll say, okay, this ranking is more or less okay. I don't like the first two books. The third and fourth books are good. And then I give another ranking. It says, oh, I like the first two books, that means that the second ranking is better than the first ranking.
so it's not like we can find the exact accuracy.
So it's not 0 or 1, right? So it lives in a spectrum. There are multiple ways to evaluate rankings. Something like you can read up things like, for example, there is this NDCG. This is cumulative normalized discounted cumulative gain or something like that. So that's how you evaluate rankings. There are other ways also. For example, precision at mean average precision. So you could do something like reciprocal rank. There are so many ways to evaluate rankings. It's not as straightforward as regression or classification. For classification, obviously you do accuracy, right? So that's easy. For regression, you obviously say how much stars are you away from the true stars. But for ranking, it's not so straightforward, right? So of course, if you get the right ranking, you had, let's say, the first 5 books were Harry Potter, Lord of the Rings, and so on, and I get that exact right, that's perfect, right? But there are multiple ways in which to be wrong. There is only one right answer, but there are multiple wrong answers. So not all wrong answers are equally wrong. That's the main idea there. And this is captured by several loss methods, right? So NDCG would say something, mean reciprocal rank would say something, mean average precision would say something. Is there a right answer? Well, really, finally, the only thing that matters is customer satisfaction, right? So finally, if a customer is more satisfied by one ranking than the other ranking, that's the right answer. That's it. Yes.
My engagement, we assume that the customer is rational.
No, there is no malicious things there. There is no such thing, but a customer might not know his or her own mind. I think that's a reasonable thing to have, right? So you can't expect each customer to be completely aware of all the books ever written and have a complete knowledge of themselves, right? So not every customer is like a pure sage, ascetic sage with all knowledge. That's not reasonable. So you have to live with whoever gives you money, right? So customer satisfaction, I mean, it doesn't matter whether you give the right answer or not. If you convince people that you've given the right answer, that's sufficient, really. Right? At least that's true for marketing and stuff like that. You don't have to give the right answer. You have to give an answer and make them convince themselves that's the right answer. That's the... Okay. Yeah. Any other questions? Okay.